In this chapter, we're going to glue the pieces we built together and build an actual block generator. We will read markup text from a file, parse the text to a document, convert the results to our HTML EDSL, generate HTML code, write it to a file. And while doing so, we'll learn how to work with I/O and how to import external libraries to process whole directories and create simple command line interfaces. One key part is missing before we can glue everything together, and that is to convert our markup data types to HTML. We'll start by creating a new module and import both the markup and the HTML modules. This time we imported the modules qualified. Qualified imports means that instead of exposing the names that we've defined in the imported module to the general module namespace, they now have to be prefixed with the module name. For example, parse becomes markup parse, and if we would have imported HTML internal qualified, we'd have to write html.internal.element, which is a bit long. We can also give the modules a new name and write HI element instead. With qualified imports, readers don't have to guess where a name comes from. Some modules are even designed to be imported qualified. For example, the APIs of many container types such as maps, sets, vectors, and similar. If you want to use multiple containers in a single module, we pretty much have to use qualified imports so that when we write a function such as singleton, which creates a container with a single value, GHC will know which singleton functions we are referring to. Some people prefer to use import lists instead of qualified imports because qualified names can be a bit verbose and noisy. Feel free to try both solutions and see which fits you better. You can see more information about imports in the wiki article. Converting a markup structure to an HTML structure is mostly straightforward at this point. We need to pattern match on the markup structure and use the relevant HTML API. Notice if we run this code, enable all the warnings, or just by looking by it, we can reveal that the pattern matching is non-exhaustive. This is because we don't currently have a way to build headings that are not H1. There are a few ways to handle this. We can ignore the warning. This will likely fail at runtime one day and the users will be sad. We can pattern match other cases and add a nice error with the error function. It has the same disadvantages, but we lose the notification at a compile time. Third, we can pattern match and do something wrong. User is still sad. Fourth, we can encode errors in the type system using either. We'll see how to do this in the later chapters. We can also restrict the input, change the markup heading to not include the number but rather specific supported headings. Well, this is a reasonable approach. And last, we can actually implement an HTML function supporting arbitrary headings. And this should be straightforward to do. Let's implement the function that takes a natural number, a title, and returns the structure for any heading, which we'll use to define arbitrary headings such as H1, H2, and so on. Okay, now we have to pass a natural, which we import from numeric.natural. Change H1 to more general H and use a number in H. And we should not forget to export it from HTML HS. Now we can fix the convert structure function using all the headings. In order to create an HTML document, we need to use HTML function. This function expects two things, a title and a structure. For a title, we could just supply it from the outside using the file name. In order to convert our markup document, which is a list of markup structures, to an HTML structure, we need to convert each markup structure and then concatenate them together. We already know how to convert each markup structure. We can use the convert structure function we wrote and map. This will provide us with the following function. To concatenate all of the HTML structure, we could try to write a recursive function. However, we will quickly run into an issue with the best case. What to do when the list is empty? We could just provide a dummy structure that represents an empty HTML structure. We can add it to HTML internal and call it empty. Now we can write our recursive function. We have a list of structure, and if we have one element, we take one element out and append it to the rest of the elements. If the list is empty, we return empty. Remember the append functions that we implemented as an instance of semigroup type class? We mentioned that semigroup is an abstraction for things that implement append operation, where append is associative. It turns out that having an instance of semigroup and also having a value that represents an empty value is fairly common pattern. For example, a string can be concatenated and the empty string can serve as an empty value. And this is actually a well-known abstraction called Monoid. And actually, empty is not a very good description of what we want and isn't very useful as an abstraction. Instead, we can describe it as an identity element, which satisfies the following laws. X appended with identity is still an X, and identity appended to an X is still an X. In other words, if we try to use the empty, this identity value, as one argument to append, we will always get the other argument back. For string type, the empty string satisfies this. This is of course true for any value we'd write, and not just world or hello. Actually, if we move out of the Haskell world for just a second, even integers with plus as an associative binary operation in place of append and 0 in place of identity member form a monoid. So integers together with a plus operation form a semigroup, and together with a 0 form a monoid. We learn new things from this. A monoid is a more specific abstraction over semigroup. It builds on it by adding a new condition, this existence of an identity member. This abstraction can be useful. We can write a general concat structure that could work for any monoid. And indeed, there exists a type class in base called Monoid, which has semigroup as a superclass. And note that this is a simplified version. The actual is a bit more complicated because of backwards compatibility and performance reasons, and semigroup was actually introduced in Haskell after Monoid. We could add an instance of Monoid for our HTML structure data type by using empty as an identity element. And now, instead of using our own concat structure, we can use the library function concat, which could theoretically be implemented as this. Pretty much what we did with our function. Notice that because semigroup is superclass of Monoid, we can still use the append operation from the semigroup class without adding the semigroup constraint. By adding the Monoid constraint, we implicitly add a semigroup constraint as well. This concat function is very similar to the concat structure function, but this one works for any monoid, including structure. Abstraction helps us identify common patterns and reuse the code. And a side note, integers with plus and zeros aren't actually an instance of monoid in Haskell. This is because integers can also form a monoid with multiply and 1, but there can only be one instance per type. Instead, two other new types exist that provide that functionality, sum and product. Let's see how they can be used in GHCI. Note that product is a data constructor. We can get the underlying integer from it using getProduct. If we have integers from 1 to 5, we can wrap them in product and concatenate them together using multiplication to get 120. We've used map and then concat twice now. Surely there has to be a function that unifies this pattern. And indeed, it's called foldMap. And it works not only for lists, but also for any data structure that can be folded or reduced into some sort of summary value. This abstraction in the type class is called Foldable. For a simpler understanding of Foldable, we can look at fold. Compare it with concat. Concat is just a specialized version of fold for lists. And fold can be used for any pair of data structures that implements foldable and a payload type that implements monoid. This could be a list with a structure, or maybe with a product integer, or your new shiny binary tree with string as the payload type. But note that foldable type must be of kind type to type. So for example, HTML cannot be a foldable. FoldMap is a function that allows us to apply a function to the payload type of the foldable type right before combining them with the append function. Compare this generic foldMap with a specialized version, where T is a list, M is the HTML structure, and A is a markup structure. True to its name, it really maps before it folds. You might pause here and think, okay, this map we are talking about is not specific to list, then maybe that's another abstraction. And yes, it's actually a very important and fundamental abstraction called functor, but we had enough abstraction for this chapter and we'll cover it later in the book. Let's finish our code by writing convert function. The convert function takes an HTML title, a markup document, and returns an HTML. First, as we just talked about, we convert all the structures using foldMap and then compose it with HTML functions that takes a title and the converted structure. Now we have a full implementation and can convert markup documents to HTML. A quick summary. We've learned about qualify imports, ways to handle errors, and monoid and foldable type classes and abstractions. In the next chapter, we are going to glue our functionality together and learn about I/O in Haskell.